Welcome. My name is Ricarda Busse, and in this presentation I will compare the Strep-tag with the His-tag and point out the benefits and drawbacks of these two purification systems. At the beginning of the webinar, I will give you a short overview on the available affinity purification systems based on peptides and proteins, and then we go into the details of the Strep-tag and the His-tag systems and compare both systems with each other. At this point, I'm interested to hear which is the major tag used in your lab. Is it the Strep-tag or the His-tag? That's pretty clear. 100% use the His-tag as a major tag. So I hope after this webinar we will change this a little bit. Okay, then we begin with the webinar. A wide range of small peptide tags are available, like the His-tag, the flag tag, the Strep-tag, the MIP-tag. And there are also some large protein tags available, like the GST tag or the MVP tag. The advantages of small tags are that they are not as immunogenic as large tags, and they do not need to be removed after affinity purification, because their influence on the protein structure or function are negligible. Small tags can also be used as epitopes for antibody production. Also, antibodies against the small peptide tags are available for immobilization and detection of the recombinant proteins. The advantages of large tags are that they may increase protein solubility, but after purification it is recommended to remove the large tag for downstream applications. Each tag is using a different purification matrix and its own purification protocol, as shown on this slide here. Whereas the common major steps for protein purification are binding, wash, and elution. When starting with the purification of a new protein, where the optimal purification conditions are unknown, you should think about different purification tags, because not all tags are suitable for all kinds of protein classes or compatible with downstream applications. For example, the His-tag is not recommended for metalloproteins, because the metal center of metalloproteins may be absorbed by the Ni-NTA matrix used for the His-tag purification. Another example is the study of enzymes. Here it is important to preserve the bioactivity of these proteins. For this, physiological buffer conditions are recommended, such as used for the Strep-tag purification. The same is true for protein-protein interaction studies. Those interactions are destroyed when high ion concentrations or low pH are used. Now we will have a look a bit more into the details of the Strep-tag purification system. The system is based on one of the strongest non-covalent binding partners in nature, which is the Strep-tactin biotin binding. The Strep-tag is a peptide optimized for the binding into the biotin binding site, and Strep-Tactin and Strep-Tactin XT are engineered Strep-Tactin variants. This allows a rapid one-step purification of recombinant proteins under physiological buffer conditions, which results in unsurpassed protein purity and bioactivity. Further, the system tolerates a broad range of detergents, chelators, salt, or redox conditions. The system is beneficial for a range of protein classes, such as metalloproteins, membrane proteins, bioactive proteins, and protein-protein interaction analysis. Further, the system is evaluated for different expression hosts, such as bacteria, mammalia, yeast, plant, and insect cells. The aforementioned high purity results from two specificity conferring steps during the purification cycle. The first specificity conferring step occurs during lysate application. It is a highly specific binding of the Strep-tag with the biotin binding site of Strep-Tactin XT. After this, the wash of the column is done under physiological buffer conditions, which preserve, for example, the bioactivity of proteins and protein-protein interactions. Then the second specificity or conferring step follows. It is a competitive elution using biotin for Strep-Tactin XT. Finally, the resin is regenerated with low-concentrated sodium hydroxide and can be reused at least 3 to 5 times. And when the column is treated properly, you can also reuse it up to 20 times. Next, we have a look at the His-tag purification system. The system makes use of the fact that several amino acids, like the histidine, form complexes with metal ions. Nickel selectively binds proteins if suitable complex-forming amino acid residues are exposed on the protein surface. Additional histidines, such as in the case of the 6S His-tag, increase the affinity for nickel ions, and due to this, it generally makes the histidine tag protein the strongest binder among other proteins on the column when you use, for example, E. coli extract or other cell extract. Then, the general procedure for the purification is that you equilibrate the column with buffer containing low concentrations of imidazole. Also, under low imidazole concentrations, the lysate is applied to the column. After this, the column is washed and the bound proteins are eluted upon addition of high imidazole concentrations. In order to improve protein purity, an imidazole gradient is recommended at this step, which requires usually automation of the purification cycle. After this, the resin can be regenerated and reused. We have compared the two purification systems regarding their purity. For this, we have purified two random proteins, namely M-cherry and GAPDH from E. coli, using either the His-tag system or the Strep-tag system. Here we have specifically used the Twin-Strep-tag in combination with Strep-Tactin XT. On the SDS gel, you see the flow-through and 3 elution steps after gravity flow purification. And the main protein portion is usually eluted, concentrated in the second elution step. For both proteins, you can clearly see that the purity after the Strep-tag purification is very high and that no further purification step would be necessary before you use the protein for further applications. In contrast, the His-tag protein show quite a lot of unspecific background proteins, and further purification steps like size exclusion or ion exchange chromatography would be necessary to increase the protein purity. This shows that highly pure protein can be obtained after a single purification step using the Strep-tag system, which is more economic and time-saving. Besides native purification of recombinant proteins, denaturing conditions are very often required when the protein is not soluble. We have also compared purification under denaturing conditions for a protein which was purified in our custom protein production facility. For the His-tag purification, we have used the standard protocol for denaturing conditions, which allows to use up to 8 molar urea. The first elution step for this protocol was done at pH 5.9, and the second elution step needs to be done at pH 4.5, which you see here. The SDS gel shows that the protein is eluted during the second low pH elution step, which is done at pH 4.5. We have compared this to a purification with 4 molar urea on Strep-Tactin, which is not suitable for denaturing conditions, as you can see, because the Strep-Tactin is not stable under these conditions. And we have used 6 molar urea on Strep-Tactin XT resin. What you see is that one elution step is sufficient to elute the protein, and that the amount and purity of the target protein is much higher compared to His-tag purification under denaturing conditions. There are some more conditions for which the Strep-tag system is beneficial over the His-tag. Those are, for example, the purification of metalloenzymes, because metal centers of those enzymes do interfere with the nickel of the Ni-NTA resin. It is beneficial for large proteins, because also for large proteins you can achieve very high purities. And it is recommended for heterodimeric proteins or multimeric membrane proteins. Because, for example, when you have heterodimeric proteins like antibody, which consists of a heavy chain or in the light chain will be co-purified because physiological buffer conditions will not destroy this interaction. The same is true for multimeric membrane proteins. Different proteins require different purification conditions, but in general you obtain a higher purity using the Strep-tag system, even under denaturing conditions and in batch purification. And no additional purification would be necessary for downstream applications using the Strep-tag system. The Strep-tag system uses physiological buffer conditions, which is beneficial, for example, for enzymes or metalloproteins or protein-protein interactions. And the system uses a mild reversibility due to the addition of biotin or desthiobiotin, which compete with the tag for the biotin binding site on Strep-Tactin or Strep-Tactin XT. The system is also beneficial for metalloproteins and for membrane proteins, and it can be used for SPR and other high affinity applications. One drawback compared to the His-tag system is that you obtain less yield compared to the His-tag if you compare, for example, 1 milliliter resin with each other. The benefits of the His-tag system is that the resin can be easily recharged and reused, and it can be used for denaturing conditions with guanidinium hydrochloride. The drawbacks of the His-tag system is that it is not suitable for metalloproteins. It interacts with complex forming amino acids, so you get lots of background proteins. You cannot use chelating agents such as EDTA and EGTA. It is also not recommended for mammalia expression because the background proteins are even higher compared to E. coli expressions. And for the His-tag, you need a time-consuming elution gradient for higher purity. In summary, the purity which you obtain from the Strep-tag system is very high. It is generally about 99%. And the purity after His-tag purification is more in the medium range, which of course both is dependent on the target protein. The buffer compatibility for the Strep-tag system is high, whereas the compatibility for the His-tag system is more in the medium range. Detergent stability for both systems is very high, and also the wash stability is very good. The affinity of the tag to the ligand is for the Twin-Strep-tag in combination with Strep-Tactin XT in the picomolar range, and for the Strep-tag2 with Strep-Tactin XT in the nanomolar range. On the other hand, we have the His-tag to Ni-NTA with a binding affinity in about 0.1 micromolar. Both systems can be used under denaturing conditions. For the Strep-tag system, you can use up to 6 molar urea, and the His-tag system can use with up to 8 molar urea and even with 6 molar guanidinium hydrochloride. The ease of use of the Strep-tag system is very high, and also the elution is very easy. On the other side, we would rate the ease of use for the His-tag system medium, because you need time-consuming imidazole gradients in order to obtain highly pure protein. Both systems can be regenerated and reused. And with this, I'm already at the end of my talk. And if you have any questions regarding the Strep-tag system, please feel free to contact our technical support under strep-tag@ebalifesciences.com.